Hey everyone, welcome back to the second video in our series on Chapter 8. In this video, we're going to be talking about a reaction that is known as acid-catalyzed hydration, which is also just called hydration sometimes. So acid-catalyzed hydration. So what this does is hydrates an alkene, right? So we think about it, it kind of makes sense. If you are getting hydrated, then you're adding water to something, right? So in this case, we are adding water across double bond. So we'll write that. So this adds H2O across a double bond. And so this reaction is Markovnikov as well, just like in the last video. And this reaction produces both enantiomers as well. And then rearrangements are possible. Okay, let's get into it. So what we have going on here is that we take an alkene like this one, okay? And then we add in water over an acid, usually it's sulfuric acid, so H2SO4. So water over H2SO4, okay? And then this is going to give us a Markovnikov alcohol that looks like this, okay? So what this means is that I'm adding water, right? So here's my OH. So water is H2O, right? So that's my H, that's my O. But the other H went where there was more hydrogens, right? The other H went right there to that carbon, okay? So just so we can kind of keep track of where everything is. So the other hydrogen went here. So there's that hydrogen, and now there's two hydrogens on this carbon, right? But again, we don't draw those because it's line angle. So I just want to be clear so that everybody knows where everything is at. So we're adding an H and we're adding an OH. The H goes where there's more hydrogens, again, because this is Markovnikov. If you want another explanation of Markovnikov, I talk about it in the addition of HX video, the hydrohalogenation. So anyway, this is kind of what we're concerned about with this reaction. So it's just water over sulfuric acid or over H3O plus. And then that just gives me my Markovnikov alcohol. Okay. So I can also do this with anything else. I can get rearrangements as well as what I wanted to say. So I can get rearrangements. So if I have two methyls there and my double bond there, and then I add in water over H2SO4, then I get a methyl shift, right? So I can get a methyl shift in this. So then that means that my alcohol is going to add here, and then I also get this, right? And then I guess to be more correct, we should say that we get this on a wedge and a dash. So we get this on a wedge, and we get this on a dash. And then we also get the other product as well, right? So we get both of these enantiomers here because it's a chiral center that we're forming, okay? This methyl here is also a chiral center, but we also get this on a wedge and a dash, but then there'd just be a whole bunch of stuff going on. So we're not worried about that. All I'm saying is that we get this on a wedge and a dash, and this does its own thing. So we can have hydride shifts, methyl shifts, rearrangements, all that kind of stuff in this, right? So let's take a look at the mechanism for this. So we're going to do the mechanism for both of these, and then that's all we really need to say about this reaction. But this is a important mechanism that I would know. I would know all the details about this mechanism. So I would definitely study this one. Okay, definitely study this one. Well, before I get directly into this one here, so the first thing that needs to happen is that we take our water and our sulfuric acid and react them. Okay, so sulfuric acid. Got to draw all of our electron pairs and everything. Okay, so this is our sulfuric acid, and then this is our water. And if you remember, we did this exact same thing in the dehydration mechanism, right? We had to protonate water to get hydronium. So we're doing the exact same thing here, nothing different at all. So this is our first step. We need to form hydronium, and then we also get HSO4 minus, okay? So we form hydronium and HSO4 minus. So not too bad. So now we can actually do the reaction with the double bond. So just like in the last reaction that we did with hydrohalogenation, the double bond is going to act as a base, and it's going to take a hydrogen off of hydronium. And then the hydrogen is going to add where there's less hydrogens, right? Or where, excuse me, where there's more hydrogens, because this is Markovnikov, right? So that means that the hydrogen added to this carbon right here, right? So then I have a positive charge here. Okay, I have a positive charge there. And then I also formed water from this because I deprotonated hydronium, which gave me water. So now another water is going to come in, and this water is going to do basically an SN1 reaction and attach itself to that carbon. So then I have this. And then another water has to come in and deprotonate that to give me my alcohol. And then I'm done. So I get my alcohol here. And then I also get hydronium because I protonated water. So that's my mechanism for this one, okay? That's all I got to do, all right? So we form hydronium, and then hydronium gets deprotonated, and then we attack with water. That gets deprotonated, and then we're done. So we reform hydronium at the end, all right? Okay. So now let's do the mechanism for this second one, this methyl shift, just so we can see another example of a mechanism here. Okay. So then we take hydronium and we react, or not hydronium, we're forming hydronium. We take sulfuric acid and we react it with water to get hydronium. So then we get H3O plus. This first step is exactly the same. No difference at all from the last one. But now we are going to take this ring with this double bond and do the reaction. So double bond takes a hydrogen. And then the hydrogen goes onto one of the carbons, but the hydrogen is going to prefer to go on the top carbon because that carbon can go through a rearrangement. So that means that I get my positive charge here, or the hydrogen is going to prefer to go on the bottom carbon because I want a positive charge on the top carbon, because now I can have a methyl shift. Sorry. So we have a methyl shift that one of these methyls moves there, right? And then I also formed water from the last step. Okay, so one of the methyls moves there because we want to form a 3-degree carbocation, right? We only have a 2-degree carbocation right now. So we want to form 3-degree. Okay, so now I have this, and now the reaction is going to be exactly the same as this last one. So water is going to come in and attack, it's going to get deprotonated, and then I'm done. So let's go ahead and do that. So water comes in and attacks. And then what just came in is going to have to get deprotonated. By another water. So then I form my final product, which was this one, right? I form both enantiomers. And then I also get H3O plus. And that's it. So that's the entire mechanism for both of the reactions that we looked at, okay? So there's really not much else to say about this reaction. We're adding water across a double bond. It's Markovnikov. I get both enantiomers if possible, and rearrangements can happen. So it's very important to know the mechanism. So I would know that mechanism, but as long as you know those bullet points for this and you know what the reagents look like, so water over an acid, you're good. There's not much else to this reaction. So we're going to talk about 2 other types of alkene hydration in the next 2 videos. So those are oxymercuration, demercuration, and hydroboration oxidation. So those are the other 2 types of hydration, which have their own advantages and disadvantages that we will discuss in the next video. So hope you tune in for that. I appreciate you watching this one. Hopefully this was helpful, and I will see you in the next video.